Now we're going to look at the angle-angle side condition, and I'm going to start by using my Trigonometry Ultimate sketch and look at the AAS 2 tab. And we're given two angles, angle side that's going to be for angle A, an angle for angle B, and the side, little a, that's going to be opposite angle A. And so we want to make a triangle for this, and let's go to our first method of investigating. So the first thing we're going to do is make a line segment. Actually, we're going to do it the SAA. We're going to do it backwards. So we're going to make the line segment first for line segment BC that has, BC has the length of this A. See there? Okay. Next, we're going to take at the end the angle that's next to it, angle B. We're going to make this angle here at B. And so we're going to make a ray there at B. Of course, that makes a ray here and here to make the full angle. But we already know how far we're going out here. So we have two vertices of our triangle already. This one controls this angle here, so we have a certain angle. So what do we know so far? We know that the two vertices are here, and the third vertex is on this ray somewhere. Now, the question is, we don't know where point A is. It could be potentially anywhere along here. Where could it be? The thing we do know is that the angle at A is given by this angle. So once we fix that, where do we place A so that the other vertex, so vertex C has to be on this ray, but it also has to be on this ray. It's where these two cross is here. But C, on the other hand, we already know where C is. It's right here. So how many places can we get the C question mark to actually be where C is? And if you'll look, there's only one place. If we're in here too far, it's going to intersect in the middle of BC somewhere. And if you go out here too far, it's going to intersect ray BC to the right of C. Or out, C is going to be between C question mark and B. We got to make C question mark B the same as C. And if you look, somewhere in here, there's a place where it's just right, and that completes the triangle. And so that shows you that there's only one triangle. So the idea here is we use the fact that we know that it's on here, and we do this angle. Now you could do this with physical tools. It's a little bit more difficult. You could actually draw this out with a ruler here. We could draw this ray up here with using our protractor. And then using a combination of a protractor and a ruler, take your protractor, slide it along this ray, just like I'm sliding this point along here. That's sliding the center part of your protractor, and have a ruler going out here so that we keep this angle at whatever it is here, you know, and then slide it along until you get it to match, and then you can get it to work. Okay, so that's one method. Okay, so let's hide all this. And another method is to go this way. Again, we start by making our line segment, same thing, and our angle B. This time is, again, we don't know where A is, but the thing we do know is that we do know where C is. So these are all the possibilities for A along this line. The thing that's changing now is this angle. So now we know we're going from C up to A prime. We can slide this along, but we have to do what? We have to match that green angle that I'm calling A prime. This angle has got to actually be that. Well, it's too big. Oh, it's even getting bigger. Okay, let's go down here. Somewhere out here. Oh, it's too little. Somewhere in here, we want to match it. 28.81. Can I get it a little bigger? Oh, really close. I don't know if I can do it exactly. Oh, that's really close right there. So somewhere in there, though, it's just right. And we get the, where is it completed? Somehow the completed triangle's not showing up where it's supposed to be for some reason. Okay, but somewhere in there is just right. Okay, So there's sort of two ways. In both cases, we're moving A along here. We can either take the fact that we know it already goes through C and then just keep moving it until we get the angle right, or in the other way, we knew the angle was here, we had to keep moving it until it actually went through C. Let's hide a few things here. Here's kind of showing everything at once. Move this one till it lands in the right place there, and move this one until it lands in the right place there. Okay, let's hide all that. Hide that. And the next question is, are there any exceptions that could make this not work? And of course, the exception is whenever these angles are too big, then there's no way to get these things to work out. Okay? And too big means, what do I mean by too big? Well, too big is when the angle sum of the two is already larger than pi or equal to pi. Okay? And so we can come up with a theorem. If we're given any two proper angle measurements, one side length where the first angle measures to be the measure of the angle opposite the given side length, then either zero triangles are possible if the sum of the two angles is greater than or equal to pi, and one triangle is possible if the two given angle measures is less than pi. And given two triangles and two pair of corresponding congruent angles and one pair of congruent sides with the sides opposite the first pair of corresponding congruent angles, in other words the AAS condition, then the two triangles are congruent. This is the Euclidean version of this theorem. Okay, now let's look at Wesley's sketch. And he's investigating this with sliders. Now the sliders over here on the left, he has he uses the fact that we know in Euclidean geometry what that other angle is, so we can sort of ahead of time construct this without having to slide everything around like I was doing in the other investigation. But here we have an angle that's next to the vertical side. So we have this side, then we have an angle, and then we have the other angle at the top. And what we're doing is, of course, taking B, going out that ray until we get the correct angle here. But he's actually, in the construction, he's actually really using the fact that we can find this other angle and we can construct this point from that using the angle side angle condition. So in Euclidean geometry, if you're actually going to have to construct this, you would actually use the angle side angle condition and do it by first finding the measure that other angle. However, this doesn't work for hyperbolic geometry. So for hyperbolic geometry, we don't have that angle sum theorem, so we have a little bit different situation. So we start by drawing a side here, side C, and we give it a length here, and an angle here for the one that's adjacent, and then the opposite angle we have here. Now, what do we have to do? We have to move B along this ray until we get the point to match. So we're using the technique here that we are moving this along, keeping the angle fixed, and but this point here where it meets this side has got to be at C. So we keep moving it and keep moving it until what happens? Whoop, too far, too short, somewhere just right. Somewhere about there we'll make our triangle. And so at that point now we have the correct triangle that we need. Okay? So very similar to what we did. But notice, and again, there's really only one place along here where this is going to match up. You can, again, of course, mess it up. If you make the angle too big, there's no way that, no matter what you do here, it's not going to meet. Right now, it's fine. But if this angle is really big compared to this one, like that, then, well, that one's going to work. We need the sum to be, there we go. If the sum is above 180 degrees, if you'll look, there's no way, no matter how close we get, how far, those two are never going to meet. So we have really the same condition. If the two angles add up to more than 180 degrees, or pi radians, or equal to pi radians, then there's not going to be a triangle possible. So remember, in the Euclidean situation, the sum of all three angles is pi, but in hyperbolic it's even actually smaller. It's always less than pi. Okay, so let's take a look at the next version, where we're looking at it from a parameter situation. So here we can enter in some angles, two angles and a side, and this will construct it for us. Again, if these two angles add up to pi or more, then it doesn't work. Okay, and this one is it is using directional angles here, and so these are based on parameter. Once again, like all the other parts of Wesley's sketch, these angles are the same here as the ones here for hyperbolic and Euclidean, same parameters, but the S is the length in Euclidean. We use S over 10. We do a tenth of that for the length over here because of just because of the way the scale kind of works in hyperbolic geometry. It kind of works better usually. So, but if you want a specific number here, if you don't want 0.5, like if you wanted this to be 0.8, then you need to put 10 times that. You need to put 8 over here. So we can get what we want there. And again, this one you have to kind of just move around till you find the right one. So we can control these parameters and see this, and once again we see that this is just going to give us one congruence class for triangles. Again, let's go back to my trigonometry ultimate sketch for Euclidean geometry, and let's enter some things here. Let's see if we can make this thing a little bit smaller. Let's make this 7 centimeters. How about 25 degrees here and 42 there? Okay, and so this gives us a triangle, and it will construct it to scale like that. Then you can also, it computes the other angle. How it actually constructs it is it actually first computes the other angle by taking 180 degrees minus these two. This one's done in degrees. Of course, Wesley's is done in radians. And then this one, you subtract to get the other angle here. And then it's constructed really by angle side. So instead of using that, what do we do to construct it? It goes like this. You make your line segment, you make your angle at B, then you can compute your angle at for the other one, C, okay, and we work that out, and then where those two meet, we do it this way. So we basically do it with angle side angle, but we'd use it by completing the other angle, computing the other angle first. So we do that right at the beginning using the triangle angle sum theorem. Of course, that doesn't work for hyperbolic, but it works nicely for Euclidean. So we can find the other measurements by drawing it that way. So you could do that with a compass and straight edge, and then just measure the other sides. But if we wanted to compute those, here are the computations using the law of sines. Actually, law of sines is what we use. So we use the angle sum theorem here to find the other angle, and here we can solve for side B and C using the law of sines, and then find the area here. And then, of course, the areas, we can show that as well if we want to. Okay, I have the proof worked out here on the trig sketch, but let's also go over the proof right now with hyperbolic illustrations as well. Now, it's interesting when you look at this in the high school textbook, because this is usually the only one that's actually given with an actual proof. A lot of times they'll basically treat this angle side as a postulate, which they should because it is a postulate, but then they'll sometimes treat side and angle side angle as postulates as well, even though we can and we have in here proved those as theorems. But then if you take the angle side angle congruence theorem as given, whether that's a postulate or a theorem that you've already proved, an easy proof of angle side would be to use the triangle angle sum theorem to show that if they have two angles congruent, they have the other angle congruent, then the angle side angle theorem gives us congruent triangles. Perfectly good proof for Euclidean geometry, and very easy proof if you have the angle sum theorem, but we don't have that in hyperbolic or spherical geometry, and we're going to actually prove this. Now, by the way, let me see if I can get this. In spherical geometry, we do have to be careful because angle side condition does not necessarily give us what we're after. Does not give us congruent triangles. Let me see if I can find the sketch I'm after. Here we go. So here's our spherical disc, and it's interesting if I make a triangle here. Let's make some triangles, and let's make it go from this point to this point. Okay, we'll make okay, so now we just got us a triangle. Okay, and I want to make another triangle inside this one, like this. Now, watch what happens when I go all the way to the edge here if I'm at the pole. So something interesting happens right here. Let's measure some things on these triangles. Okay, so let's measure some distances. So we're going to measure that distance, and that distance, and they are the same. Now it should be pi over 2. So what is pi over 2? It's about 1.57. Okay, so let's make the circle the right size. Okay, so that should be pi over 2. Okay. Now we have these triangles, and all of these sides right here are congruent to each other. We have two triangles, well, three triangles, a little one here, and the big one here. Now, whoops. Okay, now let's look at some angles. So if this should be an angle measure. There we go. And if we do this right, those are all at 90 degrees. So I'm not quite where I need to be. Probably not quite at the center of the... So if I do this exactly right, these should all turn out to be exactly 90 degrees. I may not be able to get it exactly where I need it to be here, but I think you can see the idea. So these are basically right angles, right angles, right angles. Now when you get to this triangle, what's interesting is, notice that this triangle, we have these two, the big triangle, let's say, and this little one here, have angle, angle, and side in common. So this side, okay, and it has the angle, two right angles, and then side. So these have the angle side condition, but clearly the sides are not the same length down here, so they're clearly not congruent triangles. Angles are different in the center here. So these are, this is an example where we have angle side condition, but we do not have congruent triangles. So we have to be a little careful. Now it does turn out that it works if all the sides are small enough in length. So if we have all the lengths are less than pi over 2, then the angle side condition does work. So we're going to watch when we do our proof here that we're going to try to see there should be some point in the proof where it breaks down for spherical geometry. But it will work for hyperbolic and Euclidean, and we're going to have, again, Euclidean illustrations on the left and hyperbolic on the right. So once again, we're given triangle ABC, whether that's the hyperbolic one or the Euclidean one here. And then we're going to get a congruent, well, it's going to ultimately be congruent triangle down here. DEF, we don't know yet that it's congruent. Okay, now we want to prove these are congruent. What do we know? We know that AC is congruent to DF. Okay, so let me actually just mark that. AC and DF are congruent. And let me edit this just slightly so that these are going to show up here when we go do the proof next time. So edit, action button, high show, and we're going to name it AC equals DF. Okay, and instead of that right here, that's where we're gonna put that. We'll make it red like Wesley had it. So now when I click, I guess we should make it underlined as well, since it's clickable. Everything clickable is underlined. So now it's going to show us the marks to indicate that they're congruent. So those are typical. These are typical marks in geometry to indicate congruent sides. Of course, we're not saying that. We're saying that we're over on the right. The illustration is hyperbolic. The left is Euclidean. We're not comparing the Euclidean to hyperbolic, but we're comparing within Euclidean or within hyperbolic. And then let's go ahead and do the same thing for the angle marks C and F. Okay, so C, I can mark it here, and F here. Actually, he has that later, so. Okay. And B and E are congruent. So, alright, so on FE, So make the ray FE. There's a unique point G out here somewhere, so that FDG is congruent to CAB. So this angle here. So let's start over again. Draw the ray at FE. Okay, down here. Go out a point G, and where is this point G going to be? It's going to be so that the angle that we have here, okay, is congruent to the angle that we have at A in the original. Okay, now what we're going to know is that ultimately that's going to actually have to put it right here so that G and E have to be the same. Okay, but at this point we don't know whether that's in or out here. Now remember, we already know that angle F is congruent to angle C. And FD equals CA. We've already got that marked. And now we have this angle here. So now what do we have? We have angle, side, so angle, let's see. Oh, let's look at the Euclidean. Angle, side, and then the angle here matches the angle here, supposedly. Okay? And so that makes the triangle here at DFG congruent to ACB. Same picture over here on the right. So that's by the angle side angle theorem. Now, corresponding parts of congruent triangles so we are congruent, so we know that the angle there at G is the same as the angle at B, but we know that's the same as the angle at E. Now suppose that these are different points, like it's out here or out here. Okay? And in this case, what do we have? We have, if in one case or another, one of these is going to be, let's say if G is out here, then this angle here is congruent to this one here. Then the measure DEF, this red one here, must be strictly greater than the measure of the angle inside here. The exterior angle must be strictly greater than the remote interior angles. And this is true. This is where the proof breaks down for spherical geometry in that case I was showing you. That theorem, the remote interior angle theorem there, is not, the exterior angle theorem, is not true there for the spherical in that case. And so this is where the proof breaks down, but it does work for hyperbolic and for Euclidean geometry. We do need to be sure that we actually go back and prove that theorem. So I'll go back and prove that a little bit later, and I guess I'll insert it before this at some point. Okay. What if it's in here? Let me make this a little bigger. We can see. What if the point is on this side? Well, then the angle E here is the angle is actually on this side. It's not marked right if it's on that way. It's the one over here, and again, it's an exterior to this. So one of these two is an exterior to the other one, and they can't be the same size. The exterior one has to be greater. So that's a contradiction, and so the only way that we can fix that is to make sure that G and F are actually the same point, and that means that the triangle DGF is really DEF, and so we have proved that these two triangles are congruent. So there's our proof, and that proof, notice it did not depend on the angle sum theorem, so it is completely valid, same valid over here. The exterior angle theorem that I quoted a couple times it actually is valid in spherical geometry as well if the sides of all three sides are less than pi over 2. If that's the case, then it is also actually true, and so then this proof works in that case as well. So we do get an angle side theorem in spherical geometry if we have an extra restriction that all the sides are a length less than pi over 2. But we've of course seen an exception to that when it's not.